Hello students, in this video we want to learn about the superposition principle. In the previous video we have already learnt about Coulomb's law, but in that law we have only learnt about how to find the electrostatic force between two charges. But what will happen if we have multiple charges in the system? How do we find the force on a single particle due to the presence of multiple charges? That is what we want to find out and understand in this superposition principle. If there are multiple charges, then how do we deal with it? Because in Coulomb's law, we have only considered the case of two charges exerting electrostatic force on each other. So let us go ahead and try to understand that. Let me take a system of charges here. So we have four charges, Q1, Q2, Q3 and Q4. We want to find out what is the net electrostatic force acting on charge Q1 due to the presence of all these other charges. Alright, let me write this down. We want to find net force on Q1. What is the net force on Q1? So we know very well that every charge is going to have some interaction because these are charged particles, they have some charge. So each of the pair of charges is going to have some interaction. But how do we get the net interaction or the net force acting on charge Q1? This is where the principle of superposition or the superposition principle comes into picture. The superposition principle has two parts in it, two statements in it. Firstly, it states that the individual interaction between two charges will remain the same irrespective of the presence of any other charges. Okay, let me say it once again. The interaction between two charges or between a pair of charges will remain the same irrespective of the presence of any other charges. That means the force between Q1 and Q2 will remain the same whether there is any other charge present here or not. Whether there are two charges present here or whether there are hundreds of charges present here, the interaction force between Q1 and Q2 will still remain the same and it will be governed by Coulomb's law. Right? The second part states that the net force or the net interaction experienced by the charge Q1 or any charge will be the vector sum of all the individual interactions between the particles. So this makes things very simple. You just have to keep on applying Coulomb's law for every pair and find the individual interaction force between them. To find the net force, then you just have to do the vector sum of all these interactions, all these electrostatic forces. All right, and we know how to add vectors, right? So let's take Q1 and Q2 here, and once again for simplicity I'm going to assume that all these are positive charges. So between Q1 and Q2 there is going to be a repulsive force. Q2 exerts a force like this on Q1. This is F12, force on 1 due to particle 2. Similarly, Q3 is also going to exert a force on Q1 and that will also be a repulsive force. In this direction, F13. So to find the net force, we have to add two forces one after the other. So I'm going to add F12 and F13 using parallelogram law, and that will give the resultant as this. Okay, let's say it is some R1. So we completed the parallelogram and then the diagonal gives the resultant force R1 vector. Now there is some interaction from Q4 also, some force due to Q4 also. That will be F14 and it is in this direction. Now we have to add R1 with this F14. So again we'll construct the parallelogram and finally get the net force, that is this. So the final force that we get is the F net. The net electrostatic force acting on charge Q1, which we want to find here. Alright, so I hope the approach is clear. The individual interactions do not get affected, they remain the same. The net interaction or the net force is the vector sum of all the individual forces. Mathematically, if I want to write this, I will say F net on Q1 is equal to F12 plus F13 plus F14. Okay. Individual interactions will still be written by using Coulomb's law. So therefore, F12 is nothing but KQ1 Q2 by R12 square. So I'll put R12 vector and magnitude of it square. Direction we know it is R12 cap. Similarly, then we have to write F13, which is KQ1 Q3 upon R13 mod square, and direction is R13 cap. In fact, this way, even if I have n number of charges, not just 3, 4, 5, 10, 100, any number of charges, we can simply continue this pattern, keep on writing all the individual forces. The sum total of that will give us the net force acting on the charged particle, right? So, superposition principle is actually quite logical and simple. In fact, this is what we do everywhere wherever forces are involved. Throughout in mechanics, this is what we have always been doing. When you do problems based on laws of motion, that is what we do. We add up the vectors, we add up the forces. Let's say there is weight, normal reaction, friction, some external force. We find the net of all these forces to get the effective force on acting on one particle, or let's say a block. Same thing we are doing here also, but it is important to state this as a principle because this is a new type of force, this is electrostatic force. We need to check whether it follows superposition or not. So we are saying yes, it does. The individual interactions still follow Coulomb's law. The net force is simply the vector sum of all the individual interactions or all the individual forces. So this way, we can find the electrostatic force on any particle due to any system of charges. It can be point charges like this. It can even be continuously distributed charges. We are going to see some problems based on this multiple charge system based on superposition principle now, so that this concept becomes more clear to you. Hello students, in this video we want to take some problems based on the superposition principle. So we've already studied about this principle, which is used when we want to find the net electrostatic force or the net Coulomb force exerted by multiple charges on one charged particle. So let us go ahead and see some problems where we need to apply this superposition principle. So this is the topic which we want to take, numericals on superposition principle. Let's take the first question that we have here. So there's a question from NCERT itself, example 1.6. I'm taking. Consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge capital Q with the same sign as small q placed at the centroid of the triangle as shown in figure? So the capital Q is kept here at the centroid, right? This is how the setup is. We have three particles. So we have given them the name A, B, C. The charges are Q1, Q2, Q3, but the magnitude of all of them is equal, Q, Q, and Q. There's a fourth charge kept at the center. We have to find what will be the net force. What is the force on this charge capital Q? So we need to apply superposition principle because there are three different particles which are exerting force on this Q, and capital Q is of the same sign as small q. Therefore, all the forces will be repulsive in nature. So let me just try and show all these forces, how they will act. So starting from A, repulsive force from here will act like this. Then from B, again, we'll get a repulsive force like this. And from C, again, if we take a repulsive force, it will be like this. Okay. So this is how all the forces are acting on this particle. If we give the name, then this is FA, this is FB, and this is FC. Okay. Now, if you look at these three forces, their magnitudes are going to be the same because each charge is at the same distance, whatever the distances are, because it's the centroid of the equilateral triangle. It is also the circumcenter, and therefore the distance of this capital Q charge from every vertex is same. Since the magnitude of all these forces is same, FA, FB, FC, they have same magnitude, right? Therefore, all these vectors, when we add, they are also spaced at equal angles. The angle between any two of them is 120 degrees. And if we take three such vectors, which are of equal magnitudes and they are at 120 degrees from each other, then the net is going to be 0. They are going to cancel out. F net is going to be 0. Okay. If you do want to calculate and find out, you will have to apply parallelogram law here. So you complete the parallelogram and you'll see that the resultant of FA and FB comes out like this, which is exactly opposite to FC, and it will also be equal in magnitude to that. And that is how the net force on that charged particle becomes 0. The common mistake which may happen here is we may do this, that take only the magnitude and add up all the magnitudes. That will be absolutely wrong, and we may say that the net force is 3 times of K capital Q small q by R square. So please remember, this will be completely incorrect. This will be absolutely wrong, because force is a vector quantity and we have to do vector sum to find the net force. Right? So I hope this question was clear. Let's go ahead and take the next problem now. All right, so this is the next question that we have. This is also from NCERT example 1.7. Consider the charges Q, Q and minus Q placed at the vertices of an equilateral triangle as shown in figure. What is the force on each charge? So you can see here there are 3 charged particles, A, B and C. A and B are having a magnitude Q, whereas C is having a magnitude of minus Q. We have to find the force on each of the charge. So we have to find the force on A, B and C, each of them. So let's start with A and let's try to analyze the forces acting on it. Now, A and B are like charges, therefore the force will be repulsive in nature. So the force acting on A due to B is like this, repulsive in nature. And C and A, if we look at, then they are opposite sign. So the force between them is going to be attractive in nature. So the force will be like this, right? So we can clearly see that these two forces, they are acting at an angle of 120 degrees. This is the force on A due to B. This is the force on A due to C. Their magnitudes, if we try to find, then they are going to be the same, because each pair of charges here has the same magnitude Q, Q, and the distance is also same, that is L. Okay, so each of the force that is acting here is going to have the same magnitude F, which will be KQ square by L square. All right. Now, for finding the force on A, we need to add these two vectorically. So the resultant, if we try to find, then either you can use the resultant formula or you can take components and then add them. Okay. This is a special case, and you must remember the result of such special case, it will really save a lot of time in competitive exams when you are solving questions. If there are two forces or any two vectors which are acting at 120 degrees and their magnitude is the same, then the resultant will also be equal to that same magnitude. So the force on A, its magnitude, if we find, it is going to be simply kq square by L square. Its direction, if you want to find, you have to complete the parallelogram here and apply parallelogram law to show that the direction of final force, net force on A will be like this. Okay, so we can say it will be at an angle of 120 degree with respect to the line AB from here, or 60 degree from here. Either ways we can report it. So this was the force on A. Now for B also, if you see, the symmetry is similar to A. Okay, the distribution of forces is similar to A. A will apply a repulsive force on B like this, and C will apply an attractive force on B like this. The resultant force, if we want to find, then again parallelogram law. This will be the resultant force FB. These two are also at 120 degrees. The resultant will be at an angle of 60 degrees and so on. So FB is also going to have the same magnitude, kq square by L square. All right. So simple calculation for A and B. Two forces are there at 120 degrees having same magnitude. So the resultant also has the same value. Now let's come to C. The case for C is slightly different. I'm going to remove all this working here so that we can focus on C. So let's see how the forces are acting on the particle C. So A will exert an attractive force like this, and B is also going to exert an attractive force. These two forces are going to be at an angle of 60 degrees. All right. The resultant, if we want to find, then complete the parallelogram. The resultant will be like this, coming downwards. This will be the force on C. Okay. So now we have two forces which have the same magnitude, kq square by L square, but they are acting at an angle of 60 degree with respect to each other. So we'll have to calculate the force on C. Direction we have already specified. Okay, so magnitude of this is under root A square, which is F itself. So F square plus 2 into F cos 60 degrees. Cos 60 degrees 1 by 2. So I can substitute this cos 60 degree by 1 by 2. So this 2 will go away. We'll have F square plus F square plus F square. That is under root 3F square. And therefore, the resultant will be F root 3, or we can say root 3 kq square by L square. This will be the net force acting on the particle C, Fc, which we wanted to find. And it is downward, okay, or we can say perpendicular to the line AB, or along the angle bisector of ACB, and so on. All right. So this is how we analyze the superposition principle applied on multiple charge system. We have to look at the directions and use vector addition appropriately. Sometimes you can use vector addition directly. Sometimes you may have to use resolution of vectors and then add the components. All right. So I hope this question was also clear. We'll move to the next question and we'll take the next problem now. All right. So this question is also from NCERT, exercise 1.6. 4-point charges, QA equal to 2 microcoulomb, QB equal to -5, QC equal to 2 microcoulomb, QD equal to -5 microcoulomb are located at the corners of square ABCD of side 10 centimeters. What is the force on a charge of 1 microcoulomb placed at the center of the square? So if we draw the structure, first of all, if we draw the setup, then this is what we have. We have 4 particles kept at the vertices of this square. So one is here, second here, third here, fourth here. And this is A, B, C, D. This is A, B, C, D. Now the charge on the vertex A is 2 microcoulomb. This B is minus 5 microcoulomb. C is again 2 microcoulomb. D is minus 5 microcoulomb. We have to find what will be the force on a charge of 1 microcoulomb placed at the center of the square. So if I take a charge here which has charge 1 microcoulomb, then what will be the force on it? So let's analyze this force and let's try to find out what will be that force. So let's start from A. 2 microcoulomb and 1 microcoulomb. So they are like charges, both positive. There will be a repulsive force in this direction. So this is force due to A. B and this charge, if we see, then they are unlike charges. So the force is going to be attractive and it will be greater in strength than the force by A because there is a bigger charge, minus 5 microcoulomb. Then force due to C, if we analyze, then it is like this. Repulsive force again. And due to D, again, an attractive force this way. Okay. So, this was FA. This is FB. This is FC. And this finally FD. Now, if you carefully look at the distribution of forces, they seem to be all cancelling out. And why is this happening? That is happening because of the symmetry here. It is very important to observe that and not just blindly start adding the forces. Suppose if you don't look at the force due to C and D and just blindly start adding up the force due to A and B, then that is going to become very, very lengthy. You need to observe that here we have 2 microcoulomb, 2 microcoulomb. This charge is at the center and therefore this distance and this distance, they are going to be the same. So K Q1 Q2 by R square. The force is going to be the same. Force due to A and force due to C have same magnitude. Similarly for B and D also. Similarly for B and D. So what is going to happen due to this? Because of this, these forces are going to cancel out. A will cancel out with C, B will cancel out with D, and the net force is of course going to be 0. So the answer is simple. What is the net force on this charge? It is 0. There is no force acting on that particle, no net force. Okay, individual forces are there, but net force is 0. All right. So this was similar to the first question that we have taken. There we had triangle, equilateral triangle, 3 charges. Here we have 4 charges, but not all identical. They are kept on a square, but there is certain symmetry which is making the force on the central particle 0. All right. So I hope this question was clear to you. We'll move ahead and go to the next problem now. Okay, so this is the next question that we have now. This is a very interesting question and a very common type of question in competitive exams. Where is the neutral point for the given configuration of charges of a system? So we have a charge plus 9 microcoulomb and another charge minus 16 microcoulomb. They are separated by a distance 10 centimeters. We have to find the neutral point. Okay, that means where is a point where if I keep a charge, then it will remain at equilibrium. Okay, so first of all, where should this charge be kept? What are the possibilities? So we can keep the charge anywhere. I can keep the charge here, 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 Okay, there are so many possibilities. How do we narrow down that position of charge to find this neutral point? I cannot solve general vector form and say that the net force is 0. That will be very complicated. So what we need to do is we need to analyze each and every region one by one. Firstly, if I keep any charge which is not kept on the line joining these two particles, then you can clearly see that equilibrium or neutral point is not possible, because suppose there is a positive charge, then positive positive repulsion like this, positive negative attraction, these two forces will always be at some angle. If they are at some angle, they can never become 0. Okay, so this is not possible, this possibility is not there. Now if I keep them on the line joining the particles, let's say I keep the charge here, then let's analyze how the forces act. Let's say again there is a positive charge, then positive positive repulsion and positive negative attraction, both are coming in the same direction. So once again, it is not possible to have equilibrium or neutral point here, because two forces in same direction can never add up to give 0. So then two possibilities remain. One is to the left of this plus 9 microcoulomb, and other is to the right of this minus 16 microcoulomb. Now, for the two forces to cancel out, their magnitudes have to be equal. If I take a point to the right of this minus 16 microcoulomb, then the force of 16 microcoulomb is always going to be much greater than the force due to this 9 microcoulomb, and therefore this is not going to work. Okay, the force due to, in this condition, if I draw the force, if I draw the forces, then the force due to the 16 microcoulomb, let me write it as F16, will always be much greater than the force due to the 9 microcoulomb charge, and therefore this is also not possible. So the only possibility which remains is here. Let me just draw it again. So a particle kept here at some distance x from the 9 microcoulomb charge on the left side on the line joining these two particles. Okay, this x has to be adjusted in such a way that let's say there is a positive charge, then the repulsion due to the plus 9 microcoulomb, so this repulsion must equal the attraction by this minus 16 microcoulomb charge. The sign of this charge will not matter, because even if it is negative, the attraction repulsion simply are going to get interchanged, but the net force is still going to be 0. So in this case, this is the F due to 9 coulomb charge, this is the force due to 9 coulomb charge, whereas this is the force due to the 16 microcoulomb charge. So plus 9 and minus 16 microcoulomb charge. So for solving now, we are saying these two magnitudes must be equal. The force due to 9 microcoulomb charge must be equal in magnitude to the force due to 16 microcoulomb charge. Or I can say, let's say there is some charge Q, then K Q1 Q2 by x square has to be equal to KQ Q1 by x square has to be equal to KQ Q2 upon x plus this distance. Let's say it is d, so it will be x plus d whole square. The k cancels out, the q cancels out, so we can again see the sign of this charge is irrelevant. It does not matter. Okay, this is a very important point which you must remember. Please note that the location of neutral point is independent of the sign and magnitude of this charge small q which we are putting there. All right, so now if we continue solving, Q1 is 9 microcoulomb. I'll just write it as 9 mu. this is x square, whereas Q2 is 16 microcoulomb, so I'll write as 16 mu, and distance d is 10 centimeters, this is plus x whole square. So this mu goes away. Now to simplify this, we need to take square root on both the sides. So 10 plus x whole square, 9 into this is equal to 16x square. X has to be a positive distance because we have already concluded that it can't be on the other side. It can't be on the other side. So x has to be a positive distance. We need to take only one of the roots, and that will be, when we take square root on both the sides, then 3 into 10 plus x is equal to 4x, or 30 plus 3x is equal to 4x. X is equal to 30 centimeters. All right. So this is what we get. The distance at which we'll get the neutral point is at a distance of 30 centimeters to the left of the plus 9 microcoulomb charge on the line joining the two charges. There can be several variations of this question. They can ask, if both charges are positive, then where will be the neutral point? So in that case, neutral point will come here. If both are equal, then it will come exactly midway, and so on. So you'll see many more such questions in the assignments when you do. So I hope this was clear. This is a very common type of question that has been asked previously in competitive exams. So let's go ahead and take the next question and see what do we have in the next question. All right, so this is the next question which we have, and this is the last question that I'm going to be taking in this segment. So let's see this. Point charges plus 4q minus q and plus 4q are kept on the x-axis at points x equal to 0, x equal to alpha, or we can just say a, and x equal to 2a respectively. Then, so 4 options are there. We have to check each of them. Only minus q is in stable equilibrium, none are in equilibrium, all are in stable equilibrium, all are in unstable, or all the charges are in stable equilibrium. So let's draw the setup first of all. All the charges are lying on a straight line on the x-axis. Okay, so each of the charge is lying like this. This is the plus 4q, then minus q, then again plus 4q. And the positions are x equal to 0, x equal to a, and x equal to 2a. That means this distance is a, and this distance is also a. Okay, this is plus 4q minus q and plus 4q. Right now, because of the data that is given to us, we can clearly see that minus q charge will definitely be in equilibrium. Just look at the forces. The force from plus 4q will be like this, attractive force to the left. Due to this plus 4q also, it will be attractive. Since the magnitudes are same, the forces are also going to be the same. If I call this as F1 and this as F2, then we can clearly see that F1 and F2 will have equal magnitudes. Also, since they are in opposite direction, so the net force, okay, the net force on minus q charge is definitely going to be 0. Okay, so this directly eliminates the B option, which says that none of the charges are in equilibrium. Minus q is definitely in equilibrium. But is it in stable equilibrium? Let's check that. So stable equilibrium would mean that wherever I displace this charge, it should try to come back to the same position. Suppose I move the charge and try to bring it here. Now if I displace it here, bring it here, then it will come closer to the left charge, and therefore the force due to this left plus 4q will increase, whereas the force due to the right plus 4q will decrease. And because of this, the charge will further want to go towards left itself. So charge displaced towards left wants to go further left is unstable equilibrium. If it was stable, it should have come back. So only along the line perpendicular to this, actually it will tend to come back. Otherwise, it will tend to go away from the equilibrium position. So this option A also becomes wrong, which by logic makes the last option also wrong, because last option says that all charges are in stable equilibrium. By elimination, directly we can say option C only can be the correct answer. All the charges are in unstable equilibrium. You can check the forces on the plus 4q charges. They will come out to be net zero. So they are all in equilibrium, but all in unstable equilibrium. And that is why only option C will be the correct answer. All right. So as I had said, this kind of setup where three charges are kept, we have to find the neutral point, equilibrium, or in this case, what is the type of equilibrium? Where is the position of equilibrium? These are very common in competitive exams, even though there's a very old question, AIPMT 1988, but such questions have been regularly asked in competitive exams. So I hope that the application of superposition principle is now completely clear to you. Just go through the questions once again, if not, and practice some more questions and numericals, do the assignments. And once you're done with that, then only go to the next concept, that is electric field.